So good afternoon everyone. So till to date we have studied the different types of the lattice and undamped cases, and we try to see that how the wave propagation is happening, how the dispersion diagrams we can able to find it out, and from there we are actually try to see some of the properties that in which band the wave can able to propagate, where wave cannot able to propagate, what is the, and we have also seen the general monocouple system. And so this way we have proceed further. We have also seen how the resonance can be generated, how it can be tuned so that we can get a broader band, how the hybridization of the resonance peak can be possible, and what is the group velocity, phase velocity, that we have also discussed. So with this, now we would going ahead and let's start seeing if there is a damping present in the system, how the dispersion diagram get changed or get affected. Because in most of the mechanical system, damping is inevitable. We cannot neglect the effect of damping, and the system becomes in the non-conservative system, and there the presence of damping is inevitable. So we have to study that thing, like once we are try to realizing this type of metastructure for the real life application, we have to consider that effect. There is no other choice. So let's see how damping can actually affect the dispersion. So like we can think that, so that was our monoatomic chain, where we have the mass m and stiffness k, mass m, stiffness k, like this way. And we have seen that we can use the Bloch theorem. Like let's say this is my nth mass, this is n minus 1, this is n plus 1, so this is un, this is un minus 1, this is un plus 1. So what can I write? Un plus 1 will be equal to e to the power of minus mu times un, and un minus 1 equal to e to the power of minus I mu times un. And if I write the equation of motion for the nth mass, what can I write? I can write m un double dot plus k un. That's not k un. So k into un minus 1 plus k into un minus un plus 1, that is equal to 0. Or from here I can write it um, that is equal to 0. Now if I assume the solution as a harmonic solution, that is u equal to un e to the power of I omega t. So I can write what? I can write un double dot will be equal to minus omega square un. So this one will become minus omega square m plus k into 2 minus e to the power of I mu minus e to the power of minus I mu whole into un, that is equal to 0. So this tells this thing is equal to 0 because un cannot be 0. So that gives me the dispersion relationship. So I can write it minus m omega square plus k into 2 minus 2 cos mu, that is equal to 0. And we can write and from there we can calculate what is the cos mu. So that is my normal case, the dispersion relationship. Now if we try to do the same thing for the damping, so here now we are considering, instead of just only the spring, if we are having a spring mass, sorry, if we are having a spring and dashpot, then what is the change? So how the change will happen? Where will be the change? Will this be change? That Bloch theorem? No, there will be no change. Because we have seen the generality of the Bloch theorem, that Bloch theorem can able to take the logarithmic decrement, or like suppose if you see the exponentially decaying wave, or you can think that propagating wave, all those things can be taken care by the Bloch theorems. There the mu, it can be real, it can be imaginary, it can be complex. Like this way it can able to cater all the different cases. So Bloch theorem will be still valid whatever it is. So where change can be possible? We can see the change here. What will be added or subtracted? So addition is that you will have one term c into un dot minus un minus 1 dot plus c into un dot minus un plus 1 dot. That will be the change. So what can we get? Now here you can think we can write c. What is c? C is the damping. Okay. Now how we can write the c? We can write it in the terms of damping ratio. So c can be written as 2 xi into means if I think, sorry, just a minute. If I introduce the damping coefficient xi, that is nothing but c by cc. So what is cc? Critical damping. Critical damping is nothing but 2m omega n. So here omega n is k by m. Makes sense? So what is c? C equal to 2 xi root over of k by m into m, or 2 xi k into m. That is my c. Agreed? Then what can we do? And also you can think that we have this term, from here we are getting this. So what will be un dot? Un dot will be I omega into un. That will be simple, I omega into un. Nothing else. If this is the scenario, then what will be this equation? This equation can be written as m omega square plus I omega into c plus k into so what you can see, instead of k only, we will put k plus I omega c. So how the dispersion should look like? It will go exactly the same manner. So 1 minus cos mu will come omega square m divided by 2k into 1, or just a minute, like this. This will be my so that was my previous dispersion, and this is my new dispersion relation. Where is the prime change? The prime change is here. This term is added. That term was not there before. Now here, if you see, what is the complexity? So first and foremost point is that once we are having I omega c, now here you need to understand that this is a complex term which is getting added. Okay, so why it is complex? That means what? Phase difference. Exactly. That means there is a phase difference. Like your K is in some direction and C is some other phase. Like that phase is 90-degree lag is always represented by omega. I mean I. I is showing that 90-degree phase difference. So there is a phase difference in that. So now here, so that is good that there is a phase difference. I is coming, that's why. And most importantly, now if you think there is a phase difference, how can we solve it? Or yeah, so okay, so now if you think, does that create any problem? We already having the complex number because our mu is no longer just a real mu, it can be complex. So if there is a additionally complex number I mu or I omega c is added, it doesn't create anything new, it's okay. Okay, so it can be dealt. Okay, so now, so in this case we need to actually see the solution. You can so yeah, so we will do that in MATLAB. But if you see how this thing will look like, so if you think in the previous case we have seen that is the real value of mu and this is the imaginary value of mu with the omega. Real dispersion was going like this value was 2, it was going like that. That was the case. Agreed? All of you, once it was undamped. Now if you, and then it is also going to, here it is going to pi. This value is also coming to like that. But now if you see, once you will start introducing the damping, you will get the solution like this way. With the different value of the damping, solution will come like this. And this one also will somewhat like that. Okay. So your solution will start. So most important point here, there are 2-3 important points to be noticed. So in case of the undamped, like undamped, that is the red one. So in case of the undamped, if you see what is happening, up to omega less than 2 wave propagation. That means imaginary of the mu is equal to 0. Imaginary of the mu equal to 0 means there is no decaying term over the space. So wave is propagating thoroughly. Okay. And once it is decaying, it is completely decaying, no propagation. So like first case, it was like you have a full propagation, and second case it is like complete decay. Okay, because here the real value is become 0 or pi. 0 or pi, both the cases it is becoming 0. Okay, so both the cases the wave will either propagate or it is decay. There is no oscillatory decaying. Okay, but now what happened in case of the damped? In case of damped, what happened from the beginning? Like from beginning means from beginning, like omega just greater than 0, you can able to see that wave, like you here you will find that is not equal to 0 as well as real mu is also not equal to 0 or pi. So that means what? In the throughout the domain, you will have the solution something like this. Okay, and that thing is your imaginary of the mu. The rate of decay is basically the imaginary of the mu. So if that imaginary of the mu is less, like for example here you can see it will take longer, it will need large number of elements to get dissipated. But once you are but suppose once you are increasing the beta, then with the smaller space, it get attenuated. Agreed? Okay, that makes sense. So like this way, these things will actually going to work. Okay, so let's begin and go for the other systems and try to see that how the changes or what are the changes we can able to notice. So here, so this thing is coming. Now if you think in the next case, so once we are doing for like the monoatomic chain, sorry, biatomic chain, so that is the biatomic chain, and now here it is added. So if you think this is M, capital M, this is small m, capital M, small m, this is K1, K2, or maybe M1, M2, M1, M2. So how can we write? We can write for M1, that is like M1 UN double dot plus K1 into UN minus 1, sorry, that is UN, this is Vn minus 1, this is UN minus 1, this is Vn plus K2, sorry, this is K2 and K2 UN. So that was the case for the undamped condition. Okay, but once there is a damped, we can simply say C2 UN dot minus Vn plus 1 dot plus C, sorry, one mistake, it will be K1, it will be C1 UN dot minus, so that portion will be added only. Okay, and now if you think what is the prime problem here or what is happening here, so with K2, so as we have seen in the last case, K was replaced by K plus I omega C, and now here K1 will be replaced by K1 plus I omega C1 and K2 will be replaced by K2 plus I omega C2. So whatever was your equation previously, just instead of K1 substitute this and instead of K2 substitute this, you can get your solution. Okay, and so what you are expecting, so what can be expected from that? So that was my dispersion diagram in the last case, if you remember. There was a dispersion diagram for the undamped case. Okay, how it can be changed, where you can find the changes. So changes will be so it will be like that. So those sharp portion will start to be flattened, and that way the dispersion will come in. And most importantly, one thing always happening, that is, if you see from the very beginning, you are getting that wave has some amount of dissipation. Like your wave, like suppose if you take it here, In the first case, what happening? The wave was moving completely. There is no decaying nature. But means in case of the first case, if you see, that wave was completely going straight. But in case of this, like the black one, you can see that from the beginning of the, means for the very low frequency also, your wave will start getting attenuated, small level, because of the presence of the imaginary part, and that is causing the spatial attenuation. And why is spatial attenuation happening here? Because the system has inherently the damping. So once the system has damping, then once the, like you are oscillating, like suppose let's say you are oscillating this one and then the next one, and in this connection there is a damping and your energy is actually moving from here to here. So what happened? As there is a presence of damping, this thing cannot able to move as it is. Some amount of dissipation is automatically happening. So in case of the metamaterial, due to that periodic arrangement, we were getting a band gap. That is happening. That is there. So that is the property of the metamaterial. But this dissipation happening due to the presence of damping. Okay, like for example, if you take just a single degree freedom system, forget the metamaterial or anything, or if you take a multi-degree freedom system also, you can see that if you displace the system and if you leave it, it will start decaying because that energy will get decayed. And that thing exactly coming into picture here. Your energy will get decayed. Make sense? So this thing will be coming into picture. This will be Vn. So this thing actually happens here. So this is the additional point coming due to the presence of damping. Okay. Without that, damping would not actually create that thing. Okay, so now if you see the most interestingly, mass in mass. So if you think, so now here we are having the damping in between. Not only there, here also. So now if you see, in case of the monoatomic chain, now if you can make a small code in the MATLAB, so you can able to see that how the things can get changed. So you are just, so we just put some, we are just taking some different values of the damping, like here we are taking 0, 0 point, then the 5% and 20, up to 25%. Okay, so few graphs will come and we are taking that omega from 0 to 4 with a 0.01 variation, and we just wrote the code. Simple. So now if you see, if we just run that code, you can able to see how that changes are actually going to happen. So here you can see that the top part is our real portion of the wave number and bottom part is the imaginary part of the wave number. So you can see that real part is going like with the increasing damping, real part, that the sharpness, like it was like going at the 2, you have a complete attenuation, but that complete attenuation phenomena is also getting reduced. And here also you have certain level of propagation, like wave is still propagating with the help of damping, but your level of attenuation also get decayed with the high level of damping for the higher frequencies. But for the lower frequencies where you do not have any damping, like wave was completely going without any attenuation, there your peak start getting decayed. So you can say with the damping what is happening, your energy, what was like getting quite much captured in the high frequencies, is getting little bit more distributed form, so that in the lower frequency also you are started getting attenuation, and in higher frequency you are also again getting attenuation. But whereas in the high frequency, the previously attenuation was quite strong, but now that strength get reduced, because with the reduction of the imaginary part, it shows that your strength of the attenuation getting reduced. That means you need more number of units to get the same level of dissipation. So that is for the monoatomic chain. So here, so like in case of that monoatomic chain, like previously, if you are exciting it more than 2 hertz, I mean more than 2 frequency ratio, if you are exciting with that frequency, your wave will not able to propagate. But with the presence of damping, your wave will able to propagate. That type of things need to be checked. But its like amplitude will get reduced. That is true. So therefore, actually, you can also say that in case of the with the damping, actually your band gap is little bit, that concept is little bit getting disrupted, because you are not having that clear band gap concept that yes, here the wave is propagating, here wave is not propagating, because now you are having everywhere the wave is propagating with decaying. That clear cut distinction previously in the undamped case is no longer remain completely valid. But still, wherever you are having the propagation, still you are getting the propagation here in the damped. But yes, that intensity is getting little bit changed. Now, if you see in the mass in mass case, you can see that in the mass in mass, if you remember, like that cyan color shows the imaginary part. So at the very beginning portion, you are having a propagation completely. Then we encountered a band gap. Once the frequency was matching, you will have a very strong level of attenuation. Like in that resonating frequency, if you are exciting, everything is going captured by the resonator. Okay, but and also again after that you will get some propagation band here, and again you are getting the attenuation band. Perfect. That was the typically happening in case of the monoatomic chain. Sorry, mass in mass chain. But now once we will put this type of thing. Now here you can see very interestingly that with the attenuation, with the damping, what happening? In the beginning also you are having some attenuation, which was very similar to the monoatomic case as well. That we have find that okay, there is some attenuation happening, as well as your attenuation peak, like where you are getting a significantly high attenuation, that portion is also reduced. But what happened? That band get extended. Now you are started getting much wider range where your wave is getting attenuated. Is it okay? So again, that the logic is, and you can see that once the damping is significantly high, there what is happening? There this type of peak is almost vanished, and again that propagation band, that also vanished. So both the thing get merged by a similar type of dispersion diagram. So this clearly demonstrate that effect of damping is quite predominant, and we cannot neglect it, because there the full phenomena gets changed. Okay, so in case of the biatomic also, or the diatomic chain, you can also see that dispersion will come somewhat like this. So here your wave will go up, and you can again see that this is going down. You have a previously just a small amount of damping portion, and again you have a propagation band. So here now you can see that that portion of this point is coming quite larger, but there is still level of the attenuation is present there. So that ultimate point is where Means if you see all the dispersion of that different type of the metamaterial units, you can see that primarily your band gap concept is no longer very well valid for the case of damped scenario, because you are not having very distinctly, okay, this is propagation, this is attenuation. This type of things is not very clearly distinguishable. Some portion get mixed up, like things are getting broadened up and getting changed. Like if you remember, in the last class we have mentioned that with the number of unit cell, you can see that your transfer function get changed, its shape will change, it will evolve, but the boundary, band boundary remain exactly same. They are not getting changed. But here that concept is no longer same. Here with the increment of the damping, your band gap can also be changed or shifted, and most of the cases band gap concept may be get invalid, because throughout you can see some sort of attenuation. You are not having any wave which is propagating directly. You can see that there is some, always it is attenuating. Okay. So with this, I would wrap up this one. Thank you very much.